All right, so welcome everyone to today, April 24th session of SpaceGeekSpeak. SpaceGeekSpeak is sponsored by AAA Houston section, and everyone is welcome to this platform. We are meeting regularly on Saturday mornings from 8:30 until we have no longer questions for today. Normally it's posted until 9:30, but we do not cut at 9:30 unless there's some circumstances. Today, our speaker and our guest is Nancy Leveson. She's a professor of aeronautics and astronautics, and also professor of engineering systems at MIT. She is an elected member of the National Academy of Engineering. Professor Leveson conducts research on the topics of system safety, software safety, software and system engineering, and human-computer interaction. In 1999, she received the ACM Allen Neville Award for Outstanding Computer Science Research, and in 1995, the AAA Information Systems Award for developing the field of software safety and for promoting responsible software and system engineering practices, where life and property are at stake. In 2005, she received the ACM SIGSOFT Outstanding Research Award. She has published over 200 research papers and is author of 2 books, SafeWare, System Safety in Computers, published in 1995 by Addison Wesley, and Engineering a Safer World, published in 2012 by MIT Press. She consults extensively in many industries on the ways to prevent accidents. And it is my pleasure to invite Nancy Leveson. Nancy?
Thank you. Let me share my screen. There. Hopefully, is that it? Can you see that?
Yes, we can, Nancy.
Okay. So it's really a pleasure to speak to you this morning. I was actually involved with the NASA manned space program for 20 years. I was on ASAP and until right after the Columbia accident. And after that, I did help to write the CABE report and helped with the design of the new what was new ITA then, and as well as the early analysis of constellation. But I differed with some of the powers that be about what needed to happen about safety at NASA. So my only interactions with NASA in the last 20 years have been with the aviation safety program. So what I'm going to talk about is something that's actually we developed since about that time, around 2000, which is a totally different way to deal with safety. You've carefully thought of all the angles, you've done it 1,000 times, it comes naturally to you, and you know what you're doing, it's what you've been trained to do your whole life, nothing can possibly go wrong, right? This is, sometimes the best laid plans and things that we've done forever sometimes don't work so well or stop working after as technology changes. Let me start with my definition of safety because it's broader than I think many definitions. I think an accident, a mishap, or whatever you call it, is just a loss. Any undesired and unplanned event that results in a loss. So that includes, of course, obviously human life or injury and property damage, but it also includes things often aren't included, like environmental pollution, mission loss, loss of protected information, negative business impact, any kind of loss we can handle now. And you notice I didn't say anything about whether it's intentional or not intentional. So it includes cybersecurity. And I'm going to, everything I say about safety, and I'm mostly talking about safety, is going to also apply to security, and I'll describe that at the end. And there are obviously certain system goals that you're trying to achieve, but there are also constraints or limits on how you can achieve those goals. And I'm mostly dealing with the limits on how we achieve the goals, and just define safety as absence of losses. So what's the problem? The problem is that the current tools that people are using and NASA is using are all 50 to 65 years old. But our technology has changed. So, you look at FEMA was right after World War II, and then everything else was really developed in the 60s. But starting in the late 70s, our technology changed, and engineering changed radically. We introduced computer control into everything. There have been exponential increases in complexity, lots of new technology, and the human role in systems has changed drastically. And there's been nothing new except the stuff that we've introduced about in the last 15, 20 years. Otherwise, we're still using this stuff. And the problem is that these old techniques all assume that accidents are caused by component failures. And that was a good assumption at the time. And it still happens, but accidents have changed their nature in the meantime. Now, I'm going to give you a couple of aviation examples. Sorry, I just didn't have time to go look up some more recent space examples, but this is a Navy problem that occurred. Some Navy aircraft were ferrying missiles from one location to another, and because the pilot was just sitting there, they said, well, why don't you do something useful and execute a test of aiming at the aircraft in front, firing a dummy missile at it. The problem is that nobody knew that this was so-called smart software, and it was designed to substitute a different missile if the one that was commanded to be fired wasn't in a good position. And in this case, there was an antenna between the dummy missile and the target. So the software decided to fire a live missile instead. And if you think about that, what failed? I mean, each part of this system worked exactly the way it should. We can't even blame it on the human pilot this time. Here's one other example. This was an A320 accident in Warsaw, a Lufthansa aircraft. In the Airbus, they protect against activating the reverse thrusters when airborne. The software protects against the pilot making some kind of mistake, because obviously that would be very dangerous. But in this case, there was a lot of rain. The runway was very wet. There were hydroplaning. There's other factors made the software think that the plane hadn't landed. So the software wouldn't allow the pilot to activate the reverse thrusters, and it ran off the runway into a little small hill, and you can see it caught on fire, and you can see the result here. So in neither of these examples was there any component failure. Every component worked exactly the way it was designed to work and that the engineers expected it to work. So there's two kinds of accidents. There's this old traditional component failure accident that we're used to and still happens and we still have to deal with. But there are these new component interaction accidents that are occurring more and more often. They rise in the interactions among the components. They're related to complexity, which leads to design and system engineering errors. Nothing may have failed. And it's not really just the software itself. It's the introduction of software control allows almost unlimited complexity in our systems, and they're resulting in system design errors. And in fact, the role of software, and I looked at thousands, well, hundreds probably, of accidents in my career, and many of them involve software. And in every one of them, it wasn't a software implementation error. it was a requirements error. And if you think about it, that's what was true of those two examples. So, but we spend all our time on the design of the software, and we do things like software integrity level or level of rigor and stuff. And we say, if we just take a good job with this, building the software, it'll all be safe. But that's not going to make it safe at all under these kinds of conditions. And in fact, the problem is in the requirements. And we need to do something about the requirements. And most of our software engineering techniques only show the implementation of the requirement in the design. So our problem is that we, get rid of the controls here, that we're confusing safety and reliability. And they used to be a long time ago, 50, 60 years ago, they used to be about the same thing, and you could compare them or you treat them sort of the same, but it's no longer true. And if we look at this sort of simple Venn diagram here, we have in the green circle, we have the scenarios that involve failures in the system. And in the pink circle, we have all of the scenarios that lead to accidents or unsafe. Now, in this green part, A, unreliable, not unsafe, we have FMEA. It can handle that kind of failure. And the overlap, which is most of what handled now, is unreliable and unsafe. Everything works. Fault trees, or make a Sdpa is our new technique I'll talk about. But over in the pink, where it's unsafe but not unreliable, where there hasn't been failures, there's nothing that works today but our tools. And in this new approach that I'm going to talk about, but to do the new approach, we have to make some pretty large changes in the way we handle safety in general. So here's one other accident I want to talk about that involves thrust reversers. This was a different kind of plane. The other one was an Airbus. This is a Tupolev, a Russian plane. It had a soft touchdown that made runway contact a little later than usual. And there was a crosswind, which meant that the weight on wheels switches didn't activate and the reverse thruster system wouldn't deploy, which sounds like the other accident, except there's something a little different here. Here, the pilots believed that when they asked for the reverse thruster to deploy, that it would deploy the way it always do. But they had limited runways in space. Remember, they landed a little late. So they quickly engaged high engine power to stop quicker. But when the reverse thrusters didn't deploy, they accelerated the aircraft forwards, eventually colliding with the highway embankment. And the point here is that in complex systems, human and technical considerations cannot be isolated. They have to be analyzed and considered together, but we aren't doing that. So what we're doing mostly now is we have human factors experts, which concentrate on the screen design and the screen out. We have our software and hardware engineers that concentrate on the screen in, and we don't have anyone looking at this entire system as a whole. And it's the integrated system now that is causing the problems. The interactions between these things, not just the individual components. So we're getting a lot of problems with mode confusion, situational awareness errors, inconsistent behavior, and other things. And most of the accidents today that we're seeing are really of this type, because it's the thing we aren't used to handling. So what's the problem? The problem is complexity. And there are three ways that we can cope with complexity. One is to use analytic decomposition, which you know, I'll explain it. You've done it, you may not know it by that name. Statistics or systems theory. So let's start with analytic decomposition, because that's what most people use today. So what you do is you and this is really old. I mean, this goes back a couple hundred years to the scientific revolution, Descartes and those people. And they basically say, if you have a complex system, you break the system up into components, you analyze each of the components separately, and then you combine the results together and you get a result for the system as a whole. But there's assumptions under here that have to hold. It assumes that these components operate independently, and that they're not subject to indirect or nonlinear interactions, feedback loops, all kinds of not obvious interactions between them. And again, this used to be true. So this worked well. Things have changed. So if we look at the degree of randomness along one axis here and the degree of coupling, if the degree of randomness is at a certain level, above a certain level, we can use statistics to handle it. Systems theory is called unorganized complexity, but we can use statistics to handle our thing. But below that degree of randomness, and now there are lots of stuff in systems that aren't random anymore. Software, it's not stochastic. You can't treat it randomly. Human behavior, you can, and decision making, the things that humans are doing now, the complex decision making are not random. So if the degree of coupling, the degree of complexity is at a certain, below a certain level, you can use analytic decomposition. But there's this whole big area here, consistency, organized complexity, which is where almost all the systems we're building now are, and neither of these techniques are going to work. So the third possibility, which is what I use, is systems theory. And systems, I don't want to go into systems theory. It's about 50, 60 years old. It grew up at the same time after World War II, when we started building really complex, much more complex systems. And the old techniques didn't work. I didn't make this up. It's existed for quite some time. And the basic idea here, again, we have our process, we have components in the process, but there are certain kinds of things called emergent properties that arise from the complex interaction. They're not in the individual components. They arise from the interactions among the components. And safety and security are emergent properties. You've probably heard this phrase, and it's commonly used, that the whole is greater than the sum of its parts. That exactly explains what, in a nutshell, what systems theory deals with. And so we've got to look at the whole, and systems theory provides a way of doing that. So it was created to provide a more powerful way to deal with complexity. And basic idea is, and I'm not going to go into the math and all the other stuff, but basically the idea is, if our problem is in the interactions among the components, we have to have some way of controlling those interactions. We have ways of controlling and trying to prevent component failure, but now we've got to have this other thing, these interactions, and controlling them, both individual component behavior, but also controlling the component interactions. And you can think of this as a simple feedback control loop, where the controller issues control action and gets feedback from the process about what the state is. So what I believe is we need a paradigm change, and in the way we do safety in complex engineered systems today. And we need to change from what we've traditionally done, which is prevent failure and treating safety as a reliability problem and trying to prevent components from failing, to enforce constraints on behavior or treating safety as a control problem. If you think about it, this includes the old one, because we also are trying to prevent or constrain failures and control failures in our system, component failures, but we also have to control other things that are happening in the new technology, like software. Now, I want to explain, I don't mean that you actually have to have this physical control loop. in everything. Behavior can controlled in lots of ways, controlled by human operators, but through component failures and unsafe interaction control through system design, redundancy, interlocks, fail-safe design. Those are all the things we do today. So this includes everything we do today. It just includes more. We also control things through processes, manufacturing processes, maintenance, test, assurance, operational processes, or we control through social controls, government, regulatory, culture, insurance, and so on. Now, I talked about the safety constraints. Yeah.
Hi, good morning. Well, good afternoon in France and good morning in the United States, right?
I'm sorry, what was that? You're muted. Is someone talking because you're muted? You've got to unmute yourself. Can anyone hear that? I'm sorry, you were muted?
Okay.
Oh, there
hello.
we go. Okay.
Hello. Hi. My name is Philippe. I'm from France.
Uh-huh.
Nice to meet you.
Nice to meet you.
It's very emotional for me to talk with my American friends because I graduated from University of Pittsburgh many years ago. I got an MS in material science and engineering, but I'm here today as an auditor since software and hardware are not my majors. Okay.
Okay.
I'm a member of AIAA. I'm Philippe Meret, M-A-I-R-E-T, and I'm Associate Fellow of AIAA since 2019.
Did you have a question?
So, no, I don't have question, but I'm happy to talk to all of you.
Good. Well, welcome. So what do I mean by the forcing safety constraints? For aircraft, aircraft must maintain sufficient lift to remain airborne. For spacecraft, the spacecraft must not impact the planet with a force greater than X. Mars Polar Lander, of course, violated that one. Spacecraft must be inserted into a safe orbit around the planet, Mars Climate Orbiter, or Hitomi, the Japanese telescope reaction control system must prevent the spacecraft from spinning too fast. All of us are dealing with this public health system right now, preventing exposure of the public contaminated water, food products, and viruses. All of these things are what I mean by safety constraints, and so we have to make sure that and it sounds like hazards, and it's exactly right. It's just trying to prevent the hazards from occurring. So STAMP is just a new accident, more powerful accident loss causality model. It's based on systems theory, not reliability theory. It defines accidents and losses not as a failure problem, but as a dynamic control problem. And it turns out that this works on astoundingly complex systems. This has now been used on things that you wouldn't even think about doing a fault tree on or something. I mean, you just couldn't. The most complex systems that the Defense Department has built and is building right now are using this approach, and it works. So it would apply to Artemis and to the new safety, the new systems that and projects that NASA is doing, and it includes all the scenarios from the traditional hazard analysis, the failure events, but also these component interaction accidents, software and system design errors, human operator errors, and in fact, the entire socio-technical system, not just the technical parts. We can look at management and management flaws and management of safety. So I just want to stress that the traditional analysis techniques, what they do is provide a bunch of scenarios for losses, usually involving failure. Stamp-based analysis finds those same things, but it finds more things than the traditional analysis. And we've shown this both empirically and we have controlled experiments, and I can show it analytically, mathematically, that this is true. So what can you do with STAMP? Well, it's just a theoretical causality model. But from that, we can create new accident analysis methods, new hazard and security analysis, risk assessment, organization cultural risk assessment. We can identify leading indicators of increasing risk, use this in model-based system engineering, and so on. So let me just spend a few minutes describing what SDPA is. It stands for System Theoretic Process Analysis. It identifies the safety and security requirements and constraints. And so it does what any hazard analysis does. It identifies scenarios that lead to accidents. But this is, and then you use the results to redesign the systems to be safer. But it finds hazardous design flaws that are in addition to failures, and it includes software, hardware, humans, organizational processes. It supports the entire life cycle, designing safety in from the very beginning. It can be used before you have a design, which is not true of the techniques you're using now. We can actually use it during concept development and use it to identify the safety and security requirements, and then build those things into the design before you have a design. So you're not making changes at the late when it's disastrous to try and make changes. You can build this to be safe and secure from the very beginning. It's been used in test and assurance. For example, the Air Force uses it at Edwards Air Force Base to do flight test planning and testing. They're in Eglin, I guess. I just heard today is starting to use it. Production manufacturing, anomaly and incident investigation after an accident, operation, during operation. It has much more flexibility and applicability than what we're doing today. And so let me just explain sort of how this works. I don't have time to teach you how to do it. It doesn't take very long. It takes about a day to learn, but we haven't got a day. So what we have, remember I talked about, we have a controller and we have a controlled process. And the controller has issues control actions via actuators and gets feedback via sensors. Now this controller may be software, it may be human, it doesn't really matter. Within any controller, there is a decision-making component of deciding what control actions to issue, but there's also always a process model. This is actually well, never mind, doesn't matter. There's always a process model. That process model is just the model of the state that it thinks that this controlled process is in. And it understands that state from feedback and makes decisions based on it. Software or human-related accidents most often occur when the process model is incorrect. It's inconsistent with the real state of the process. If you look at Mars Polar Lander, the software thought, because of some noisy feedback it got from some sensors, that the spacecraft had landed. So the software turned off the descent engines before the spacecraft had landed. All right, this will capture software errors, human errors, flawed requirements. So let's look at what this would mean for those accidents I told you about, the Warsaw accident. Oh, what happened to the? Yeah, this was Warsaw. I'm sorry. The hazard here was inadequate aircraft deceleration after landing. So we have a pilot who's controlling the software in the aircraft, which is actually controlling the physical aircraft, although pilots can do some control of hardware now. So what happened? The aircraft, the sensors got feedback that indicated the plane hadn't landed. So the software controller's process model says the plane hasn't landed. The pilot's process model said the plane has landed. The pilot knows, he can see it, he's on the ground, he landed it. So he knows it's landed. The pilot issued a command to turn on the reverse thrusters. The software said, I'm going to ignore that command because I was told if we're not landed, I'm not supposed to activate the reverse thrusters, and therefore we had an accident. The same thing, similar thing, let me go through the Moscow accident. Really the same thing. The feedback said it hadn't landed. The software thought it hadn't landed. The pilot said it had and tried to gauge the reverse thrusters, and the software ignored that command. But something happened a little different here. The pilot said, well, the reverse thrusters are going to come on. Therefore, and I have a short runway. I need more power to stop. Therefore, I'm going to engage high engine power. But the software controller said, well, I'll ignore the reverse thruster command, but no one told me not to engage the high engine power, so it did. So we can explain and understand these accidents in using this kind of a model. And this is sort of how the analysis is done, but it's not after the fact. I mean, we don't know what happened in this. How do we find this problem? Well, we were doing a comparison or evaluation of Sdpa with the standard way, R4761, which is how they certify airworthiness of commercial aircraft. And we found this scenario, and we thought, well, could that scenario happen? You know, it seems a little weird. So we looked around the web and to see if it ever had happened, and we found many instances in different types of aircraft where this exact scenario happened. And the problem is that the standard reason in all these aircraft is that the standard hazard analysis can't find it because there were no component failures. So how do we do analysis with Sdpa? Well, there are 4 types. We start with the control actions. There are 4 general types of unsafe control actions. Control commands required for safety aren't given. Unsafe ones are given. Potentially safe ones are given too early or too late, or control stops too soon. And what we do in the analysis is identify the potential unsafe control actions, identify why they might be or were given, and then eliminate or mitigate them in our design. But there's one other thing. The controller may do the safe thing. It may give safe instructions, but they aren't followed. For example, it says to turn on the descent engines or whatever, but it doesn't. And that's usually a kind of failure in the control process. So that's how we find the traditional kinds of problems. Now, we realize that this is too simplistic for human controllers. So we've made this much more sophisticated, and this is being used. Human factors people really like this in industry. For example, GM now will not release a car unless there has been what it does is allow the human factors people to interact and talk to the engineers together and work on these things. And as I said, GM now has a policy. They will not release a car that has any kind of new human automation interaction thing unless it's undergone Sdpa. The analysis is done on control structures, which are more complex than the one I showed. This is one we're working on right now with the Army. It has to do with the new Army future vertical lift. Helicopters, both manned and unmanned, and they're going to work together in complex kinds of systems. I'm just showing you, this is the kind of it works on a model. It's not a model in a head like fault trees. There's a actual model on paper that we use. And what kinds of analysis when we do? Well, here I actually created a last I created a more spacecraft kind of example. Simplified, we have a ground station, we have a spacecraft which has scientific instruments on it, also has attitude orbit control system, mostly software now, and a reaction control system, which is the hardware, and the software is controlling that hardware. And what we can do is look and analyze for software hardware interaction. We can analyze the human automation interaction. We can analyze the human hardware interaction. And we can even look at the human-human interactions, for example, mission control manufacturers and NASA. So we can look at management issues too. What about security? Well, we treat security in exactly the same way, using the same analysis. Both are concerned with losses. One has an unintentional loss, one's an unintentional losses, but they're all losses. And the problem is that most security techniques now don't work, and because they just try and keep people out, and you can't keep people out, period. If they want to get into a computer, they will get into your computer. And they also, most techniques focus on information protection, but your problem at NASA is not information protection. You're not trying to keep people from stealing the social security number of the astronaut. What you're trying to do is looking at mission assurance, and that's what this will do. So what we want to do in the security here is ensure that critical functions and services are maintained. So this new paradigm for safety works for security too. You may have to add new causes, but the rest of the process is exactly the same. This is being done by the Air Force right now on the new ground-based security, ground-based strategic deterrence, GBSD project, which is the replacement of the Minuteman missile system. And they are using just this. They're early, they're adding requirements for safety and security, and they're going to build safety and security in early. It's basically a top-down system engineering approach to designing safety and security into systems. Is it being used? Well, it's being used just about everywhere now, except NASA space program. Aviation, automobiles, and defense are using it the most. Virtually all the automobile companies are using this, and especially the autonomous automobile companies, except for Tesla. He's a little bit, well, he thinks he knows everything. But it's used in just about everything else. A little bit in space. JAXA is using it and has used it for 20 years since we started developing this stuff. And ESA, I understand, is using it. I really don't know who's using it because it's gotten away from me. This is not just an academic technique. This has now become industry standard. We had a workshop this summer, every year. Last summer, we had 2,316 people registered from 78 countries in the world. There are standards, both auto, aircraft, and defense, that have been created or in development for Sdpa. Does it work? Well, there have been hundreds of evaluations and comparisons with traditional approaches. Some of these evaluations have been controlled scientific evaluations. Some have just been empirical industry comparing two projects or a project doing it both ways. Everyone has shown that Sdpa is better in terms of identifying more critical requirements and design flaws. It's identified real accidents that the other methods miss. And what surprised me most is that it turns out to be orders of magnitude cheaper and fewer resources than the traditional techniques. And when I first saw this data come in, I thought, that can't be true. It's more powerful. How can it possibly be? It finds everything the old does, plus it's got to be more expensive. And it turns out so we stayed studying this because I didn't believe it, and it is true. It takes weeks versus months, months versus years in comparison. And it turns out the reason it's cheaper is that we changed the paradigm, that we do it so totally differently than was done in the past. It can be cheaper. Return on investment estimates are only beginning. Most companies don't like to talk about this data. One large defense industry contractor, who won't let me use their name, claims that they saved billions by using Sdpa. So conclusions, I am going to stop and let you ask questions. I believe the manned space program needs more sophisticated tools than you're using now. If you're going to be successful, this is an astoundingly complex, important project, and you're going to have to use new hazard analysis and design techniques unless you're going to not use any software, which of course is ridiculous. We don't do that anymore in our system. I did talk about safety management, but safety management of these very complex systems is very difficult. And NASA used to have control over safety of their contractors. I don't know what's happening now. I'm a little concerned that safety is being offloaded onto the contractors. If that's true, this isn't going to work because these systems are not independent and somebody has to control all the interactions, and that's going to have to be NASA. And you can't do it any other way. Maybe you are, and I'll be very relieved to hear that. But what we're going to require to do this successfully is a paradigm change from what we're now doing. We need to handle not only hardware failures, but system and software requirements errors, system and software design errors. And we're going to have to manage a very complex system engineering effort. And to do this, you can't build something and then analyze. It's not going to work. We need to focus on building safety and security in rather than assuring it or measuring it after the design is completed. Abraham Lincoln had a quote, "The best way to predict the future is to create it." If you want more information, we have a website with papers, presentations from conferences, tutorial slides, theses, dissertations, all kinds of examples. I have a book, Engineering a Safer World, was published in 2012. You can get a free download. I made a deal with a publisher, which is MIT Press, if you go to their website, you can get a free download. It's a little hard to find. They've hidden it because they don't want to encourage it, but it's there. And if not, write me and I'll send you a PDF copy. We have an Sdpa Handbook, which we put up on the web in March 2018. As a couple of months ago, when I checked, there have been over 100,000 downloads of this handbook. It's been translated into Japanese, Chinese, and Korean versions, just by engineers in those countries volunteered, just asked us if they could translate it, and we said sure, and we put it up on our website. This CAST is another technique. It's for investigating accidents after the fact and incidents, and that's newer. It's only now been translated into Korean. I've only had this up for a short while now, and I don't have the data on how many times it's been downloaded. So that's my pitch. And I'm open to questions or discussion.
Svetlana? Hello?
Hello, yeah, we can hear somebody.
Yes, Svetlana, I have 3 different questions. It might take a couple of minutes. I wanted to get some comments from Dr. Leveson.
Yeah, Kumar.
Yes.
Kumar, we had a question from John first. If you don't mind, we'll start with that.
And then tell me, okay? Tell me. It will take about 2-3 minutes. Okay.
Okay. So maybe it's similar question. So yeah, let's start. Well, first of all, I wanted to thank Nancy. Right. It was absolutely amazing, and I was jotting down some of the notes because it's applicable in so many ways to the work that we do right now actively at NASA, both on the Gateway as well as on the acting program ISF. And I was chatting with some of the attendees as well. So it's absolutely amazing. Thank you so much for the material, and I will be downloading, so you definitely will have a few additional downloads on your statistics edit. With that said, I have a couple questions from John first, and then Kumar will ask his questions as well. How would you update safety procedures other than PRA updates? And for specifically, if there are any updates should be done for return to the moon for the gateway.
What was the first part? Sorry.
How would you update safety procedures in addition to PRA updates?
I'm sorry, I missed that. Is anyone using this, or is this applicable, did you say?
Well, so current procedures for safety procedures are using PRA for the assessment.
Oh, right. I tried to avoid that. That's where I got kicked out of NASA. So I objected to it. So yes, it doesn't work. It never worked. And there have been 2 scientific evaluations, only 2 in the last 50 years. Both of them were abject failures. Every accident I've ever seen, and there's hundreds, had a PRA that showed that accident couldn't happen. It just, in the 2 scientific evaluations, experts looking at the exact same system independently came up with orders of magnitude difference. I just got called went to UK, well, not just, because not in the last year, but a little over a year ago, I went to the UK. They were building a drone, and the Ministry of Defense, and they said that they'd done a PRA on this, which the Ministry of Defense in the UK required, and it said it was 10 to the minus 12, which turned out that, given the units, it was about not an accident, not for 500,000 years. I mean, this thing was never supposed to have an accident. And it crashed 5 times in the first year of use. And they said, please come and help us. It convinced the Ministry of Defense to use Sdpa instead, because we can't keep losing all these drones. We're not finding these problems with PRA, and PRA isn't working. So I know that that's really probably unpopular. As I said, it got me into exile from the NASA manned space program 20 years ago. But it just doesn't, it's not going to work. And it doesn't handle software. It looks at failures. So is that what? So what was your question? Now that you may have heard my rant, I'll get off my soapbox. And what was? Yeah.
The question was that if instead of PRA, what would you include? And I think your presentation overall, that's what you should include, right? Basically.
This is what we do. We don't do PRA. We do have risk assessment tools, but you can't just use probabilities because they assess risk, because these things aren't stochastic. Software doesn't fail randomly. It's deterministic. So how could you use probabilities? You don't even have this history of these things because it's new. And so you're not going to be able to use historical data even. So you're not going to get these probabilities. And the system hasn't failed. Remember, it works exactly the way in those accidents I told you, works exactly the way each component that were expected to work. So PRA is not going to work for that. You're going to have to do, and as I say, NASA's one of the few places not using this now, or even experimenting with it in the manned space program. Aviation safety, again, I've been working with them, and they're doing it, using it there. You're going to have to, it's unfortunate, because we have all these old tools that we've been which were developed, but they don't work anymore. Even nuclear power, which was all PRA, and where NASA imported, when they started doing PRA after Columbia imported people from the nuclear power industry, they're going to SDPA, and the the government agency wants to use PRA because it's a nice, easy way to certify nuclear power plants. But the industry folks said, no, this isn't going to work. We've got all this digital instrumentation in these things. We want to use Sdpa. So there's actually a fight, and nuclear is starting to use this even.
And that's interesting. I will definitely need to equip myself with a little bit more information, because this is the first time, one of the first times when I had an introduction to Sdpa. Question again from John, that he was asking if you're working with any of the current developers of the, for instance, 2 US modules, and perhaps if they are employing the same type of approach.
No, we are not working. I work with Boeing, but other parts of Boeing, Boeing Defense, not Boeing Space, and commercial going to start using it too after the MAX debacle. We don't work with any of them. I've had some students at MIT from other space companies. I'm not allowed to say the names because nobody wants me to talk about these things. It's really interesting because I go into companies and they tell me, well, we're using Sdpa, but don't tell anyone because it's our competitive advantage. And I sort of chuckle because everyone's telling me that. All their competitors are also telling me that, but not in space. SpaceX and Elon and Tesla, one of the only, again, auto companies also. So SpaceX, as far as I know, is not using it. The space industry has been the slowest. There's a couple, they aren't in Artemis. There's some, I can't say the names, but there's somebody building a launcher that's used it. And I don't know whether they still are or don't. They've done some stuff with it.
Okay, not an issue. Definitely not an issue.
And NASA needs to do that. NASA needs to, the headquarters, whoever is running Artemis at headquarters, the project itself got to do this at the system level for between the components. Because it's not just SpaceX, it's it's the SLS. There's all these other components, which has to be handled at the system level, and they're going to have to control and make sure that their contractors are implementing the safety requirements and constraints that are generated through this kind of analysis.
Now, that is a very good concept, a good approach. I have a question from Gary Johnson. He's asking if, in your opinion, how this approach would be applicable specifically for use in human spacecraft.
Oh, it's perfect for human spacecraft. Because it includes the humans. It's going to include the astronauts, and they're still going to have to do something on these. I know that you're going to try and automate most of it, but this perfect for human spacecraft.
Nancy, yes, I was very impressed with your presentation, and unfortunately, to the best of my knowledge right now, NASA's still using those old processes. And so I was very, matter of fact, I'm still working part-time with in support of the SAIC Flight Safety Office that supports the JSC Flight Safety Office. I'd like to go back and not only show them your presentation, but see if we could line up and have you go through your presentation with them. And I've got a couple of examples that popped out with me. Number one is, of course, SpaceX commercial spacecraft are heavily automated.
Right.
And NASA, going back to your concern you raised, Nancy, Nancy is had been basically backed off on terms of imposing requirements or in-depth knowledge of their hardware design and so forth, as well as the software. And so the safety reviews that NASA is still responsible to do really consist of, those people submitting hazard reports and going through some board like the Space Station Control Board and determining if the controls and mitigations are accurate. So that's the old process. It doesn't get into what you're talking about. And I just recently have come across a concern with the SpaceX. I didn't realize till just lately, and the Russians didn't either, that the SpaceX, when they jettison their trunk, which is the back end of it, they do that while they're still on orbit. They do that before they do the deorbit burn. And I just heard that trunk stays in orbit for 2 years. And those things are building up now. The Russians obviously are concerned that you're in an orbit with that trunk fairly close to space station. And so then you go back, well, the safety panel that NASA uses, they mainly address the hazards around the space station and probably didn't even ask or look at, okay, what are the hazards that SpaceX is doing when they're away from station getting ready to come back? And so I'm concerned that this hazard of close proximity to this for collision processes, if Russian vehicles go up or what have you, is being overlooked. But your process you talk about here would take those into account. And you look at SpaceX software, and we just recently had a crash here in Houston with one of their Tesla cars that killed the 2 people involved, one of which was a doctor. And nobody was in the passenger seat when it was being driven. Consumers Reports ran a test that showed, even though Tesla puts in a requirement or insists that a passenger be present when you're in automatic operation, it's obvious, according to Consumers Reports tests, they don't have any sensors or backup to determine that you truly have a passenger in the passenger seat. So this process you talk about here, Nancy, would take that into account, because it goes back to where you were talking about, this critical function that you want performed and protected or controlled. In this case, you want a passenger in the seat. And the question is, their present design, I'm sure, worked just fine. It's just they didn't have this this other available to look at it.
Gary,
Gary,
I think
just-
so
let
me just respond to that. First of all, I said Jax has been working with us for a very long time. HTV uses this and has used this.
Oh, good.
And not for Hitomi. That wasn't our problem. We could have found Hitomi problem. That should never have happened. I mean, that was so easy to find. It was a problem. It was a clear control problem. They got bad information about the speed of rotation of the telescope and spacecraft, and so they thought it was spinning slower than it was, and so they kept giving speed up instructions and lost their solar panel. I mean, that's just made this kind of problem. I've looked at I only what the newspapers have said about the SpaceX problem, software problem errors. We could have found that again, simple kind of thing. We find those kinds of timing errors and the kind of problems that happen. And I can say this with authority because we do it all the time. I did some Navy system, and they'd had an accident in tests in this Navy system, a secret system, so I can't talk about it. But they had some accidents. We analyzed the accidents, but we did Sdpa on the whole system. It had been gone through all the military, standard military processes, fault trees, PRA, all the stuff that they did, the same stuff. And I told them about these extra things we found, what's related to software. It's a very highly automated system. And the admiral said, well, little lady, I've been called that for a long time. Well, little lady, we don't need your fancy stuff. We've got PRA. We've used PRA for 40 years and it works just fine. And I said, all right, not my system. He put it into operation and it immediately ran into a nuclear, caused extensive damage on a nuclear submarine, which is enough damage it made the newspaper. So I called my friends in the Navy. I said, what happened? And they told me the scenario. And I said, we told you about that one. You know, we found it for you. And they said, yeah, but we didn't fix it. This happens all the time. There was a comparison by EPRI, the Electric Power Research Institute. They took a design of a nuclear power plant safety system, and they gave it the design to PRA experts, to fault tree experts, to vent tree experts, everything. And then they gave it to a couple of my students to do. And in 2 weeks, we provided the Sdpa for them. And it turned out they hadn't told anyone there had been an accident in this plant, a serious accident, but nobody's saying it. Sdpa was the only one that found it. So we are finding things and that are causing accidents, and exactly the things I'm reading about from SpaceX, that problem. We theoretically, I can't guarantee. It's always in hindsight. It's always say, hey, yeah, we would have found it, but we should have found it. It was capable of finding that, and as I said, this is pretty popular outside NASA. And what you're doing is so complex. I mean, this is really exciting, but an engineering challenge, a real challenge. And you're going to have, I believe, this is my belief, NASA's going to have to step up to this challenge if they're really going to be successful.
I agree, Nancy, very much. So if you don't mind, you might be getting, if I'm successful in convincing my group back there that this old graybeard says there's a new technique out there that's much better than what we've been doing, and hopefully they buy into that. We may be calling you.
Great. We'd love to help.
Gary?
I worked at NASA for 20 years. I'm in an aerospace engineering department at MIT. I work with the space people and students there, and so
I was glad to meet you because I was well aware of your name, Nancy, because I was aware that you had served on the ASAP and everything. So for the software end of it. So I was aware of that, but I really never had a chance to, meet you and hear about
I've heard your name too. It's nice to meet you. You're also a legend at NASA. I know.
I want to remind that this program has been recorded, and I will post it on the YouTube, as well as we'll send the link. So hopefully that this initial introduction will initiate some additional interaction between various groups at NASA, at GSC, as well as outside of within the greater AAA community. But it's very informative.
Thank you very much for that.
It's a pleasure.
I know that Kumar wanted to ask a question. Kumar, if you're still in, I'm unmuting you.
Okay, I have 3 questions, Svetlana. I don't know, it might take about 3 minutes or so. Is it okay? Do we have that time? I don't have to ask questions.
It's early morning here in Seattle. I don't have anything more to do than drink more of my coffee.
Go ahead and ask questions. Kumar.
Okay, Dr. Levison, first of all, I am excited to hear you, and we need new approaches, definitely, for everything. I have not been in safety in NASA. I have been in science and technology. So I have three things that I would like you to comment on. First, Mars, and I have a specific reason to ask that question to you. Second, science and technology, and third, automation. So let's go with the first, Mars. I'm very concerned about Mars dust storms. My concern stems from the fact that over here on the Earth, much of atmospheric turbulence, so to say, or storms, we have still long ways to go to model them. But on the Mars, to my knowledge, nobody has taken the effort to model the Mars dust storms, how much dust vertically they carry, what the density is, what the velocity of dust particles is. So what I wanted to ask you is, I have developed in the last 10 years, a couple of mathematical models which are based on non-linear equations. Is there anybody at MIT that might be interested? Can you help to link me with somebody that can critically look at my mathematical models, and maybe we can together develop a better description of Mars dust storms based on mathematics?
Well, I think you have to contact the MIT faculty in space. They're all astoundingly busy. Many of them are working on parts of Artemis and Mars. You know, the new experiment they just to make oxygen, MOXIE, that's what it's called. MOXIE came from MIT, and there's lots of people working on these problems there. But you know, you have to contact them
Okay,
directly.
I will do that. Let me move on to the second one, because I know there are many other questions from other colleagues. So I'll move on to the second one. Because I have been in science and technology all my life with NASA, my take on accidents is that we don't have a complete understanding of the building something that will work in the environment. And I will give you an example of the spark we had in Apollo 1, the O-ring we had that shrunk, and of course the heat shield that fell. So from my world of science and technology, I see it as a failure of technology, because you had such a cold environment at Kennedy Space Center, and your components were not ready to take that environment. This is the concern I have with the Mars dust storms. So I wanted to get your reaction to that we don't have great mathematical models of, for example, windstorms on the Earth. Their densities, there are so many parameters into these. But specifically on Apollo 1, Challenger, and the heat shield falling out, I see that our limitation on technology. I just wanted to get your comment on that.
Well, it's a lot to comment on. I'm certainly not an expert in those things. I do want to mention, I wrote a paper. I've written a couple papers that might interest all of you. One was on why the Challenger and Columbia accident occurred and the similarities, and my view of why. But there's another one that may be even more relevant that I wrote on. I was asked to write on the retirement of the shuttle. There was a book called The Legacy of the Space Shuttle. And I was asked to write a chapter on the software. And I talked about the software and why it was so successful on the shuttle and what they did to make it successful. And also went back to Apollo and some of the previous programs to talk about how NASA had learned over the years how to manage these projects. And shuttle was incredibly successful because of that, learning about that management. And I'm concerned and how to deal with suffer. And I'm concerned that they've lost that now. It's been too long of not doing anything, 20 years since Columbia, and or more, 25 years. And it's just, I think they've lost what they need to know. And in this chapter, I talk about what NASA did for the shuttle, especially with respect to software, because that's why I was asked to write about, because I was involved in that program a lot.
Right. So a lot of people think that, we have components that we need to pay attention, like this O-ring, therefore I should not have launched on that day. Kumar is different. I'm a technologist. I'm saying we can and should be launching on any day, any time, in any environment. And that's the promise of science and technology. That's where we want to take it to next level. But anyhow, I don't want to debate on that. The last one, my favorite one, is when I came to work for NASA 1965, not directly through a university, to this date, I'm still working, although I am retired. What I realized is how little tools we had. Let me give you two examples. One is the state space analysis methods, mathematical methods, that allowed us to see into the black box and then go to the component level in those black boxes and analyze, for example, the rise of temperature or something else, loss due to I square or loss or whatever it is. So that state space approach has therefore extended our reach in terms of analyzing inside complex systems what happens. Let me give you another example. We have been stuck with cosine square transform for 100 years, the way we have done data processing with sines and cosines. It turns out that processing method works if you have periodic signals. But when you are programming a system that has abrupt changes in voltage, in movement, or anything else, the cosine square transform is inadequate, will not work, will cause a lot of accidents. So came back wavelet processing of data. Beautiful. Ingrid Dabachees, 1988 or something. My point is, when we deal with automation, what I have seen over and over again when I have reviewed the papers in journals, two big problems. A, the mathematical model is wrong. B, the mathematical model is being applied beyond its domain of applicability. If you have heat equations and you're trying to go to 8,000 degrees Fahrenheit with a heat equation from Fourier, you are not going to make it. You have to have a different methodology or heat equation. I rest my case. Therefore, I see quite a bit of limitation comes from how we can model things and what physics, mathematics, chemistry, biology we have at hand. I wanted your comment on this. I'm sorry I took so much time.
Okay, well, I'm not quite sure where to start commenting. I think, you made a statement.
My point to you is, last point, I rest my case, that no matter how hard you work on safety and everything, and you definitely should. I mean, I have contributed my 10 cents work for the modeling of shuttle safety, and where we came at the end with 2 or 3% probability. In other words, in 100 flights or 105 flights, you will have 2 or 3 flights that may not make it. But my point is, the point I was trying to make with you is we transfer human intelligence to machines. That's how we automate things. And part of the reason why our crews never used automated landing on the shuttle, I have friends, astronaut friends, is because they don't trust it. They don't trust the mathematics. They don't trust that we have the knowledge to model things. That's what I wanted to tell you.
So, first of all, we can't get rid of all losses. I don't pretend to say that we're going to find everything and that we're going to make everything totally safe. As long as we we want to stretch our ambition and do these kinds of very complex but worthy projects, there's always some possibility of loss. And what we need to do, I believe, is do our best and devote as much attention as we can to preventing those kinds of losses. But there's always some risk, especially in activities like space. So I think I can improve the safety and security. I don't think I can make it 100%. If we did, you would then say, oh, good, we can do more. We can take more risks, do more risky things. Because look, we just got rid of it. This is just human nature. But the problem of handling risk is not just a mathematical, and it's not just even an engineering one. It's a management one. It's culture. Culture plays a big part in the risk that we take and the things that we do. And so unless you tackle it from all of these perspectives, not just mathematically, not just probabilistically, which I doesn't work for non-probabilistic stuff, but we have to tackle these as a whole system problem, and that will enhance our ability to successfully complete these kinds of extraordinarily exciting projects, but challenging.
Thank you so much.
Thank you. I was just responded in the chat window to somebody, there's a little chat about what happened in Challenger. And again, the same thing. You can look at it technically, you can look at it managerially, you can look at it culturally. There were a lot of pressures, external pressures on NASA, both in Challenger and in Columbia, which were the same kinds of external pressures. And NASA didn't, fell prey to those pressures each time. After an accident, you back up, you become very conservative, and then you start to drift toward the same kinds of things because you become overconfident. That you haven't had an accident for a while, so you think you can't. I was on ASAP. I mean, I know all the problems that were happening with before Columbia and the
NASA is always overly criticized for doing too much for safety and doing not enough. And unfortunately, being government entity, it's very difficult to find a balance. And especially in times of accidents, the blame goes into not doing enough. But when there's a long period of no accidents, it's the opposite. It's the other side of the pendulum, that you are too overly concerned about accidents and over safety. Like right now, is very common to say, look what SpaceX is doing and follow the same model. And it's a little, I'm not going to comment on anything underlining and whatever. I have no idea what SpaceX is doing. I just hear that. And to me, is that it's the negative side of that, saying that what NASA has been doing is not enough. However, others are doing more or less. So we need to come with a system of systems approach like you're recommending.
And it's not a matter of too much. You can do a lot of stuff that's useless. And you're just wasting resources then. As I said, we keep finding out it's much cheaper to use this and find these problems. It's much cheaper. We're looking at the Army helicopter, I told retrovertical lift, and we're getting this stuff, thousands of pages of stuff from industry contractors on this, and that has analysis. I mean, it's giving us headaches trying to go through all of this stuff. Nobody does in the government, of course. That's part of the game. You know, you give tons of stuff that nobody can review. They're spending an enormous amount, and they're missing all the problems that we're finding. So that we found with 2 graduate students in 3 months, and they have dozens of people producing all this paper. So it's not a matter of amount, it's doing the right thing. You can waste a lot of resources doing the wrong things. We did an analysis. One of the first things Sdpa was used on was the US missile defense system, one of the most complex systems ever built. And well, before some of our new ones now that we're doing now, but this was 2005, and it was very complex for them. And we had 2 people. They had been doing this for 20 years. They had done everything they could, but you couldn't do the whole system with fault rate or with PRM. It would have been stupid. Nobody could have done it. We looked at the whole system. We had 2 people, 5 months. This was right before deployment and test. It was too late. They should have done this earlier. It was right before field deployment and fielding and field tests of this thing. 2 people, 5 months. Most of the time was spent in trying to learn this because they didn't know anything about the system. We found so many errors, those 2 people, and so many paths the inadvertent launch that deployment was delayed for 6 months, and they spent an amount of money I'm not allowed to say, but a very large amount of money just fixing the problems that those 2 people found. And they told me, they said, all we found was the low-hanging fruit. I mean, there were lots of problems we just couldn't get into in the 5 months we had. It's doing the right stuff. It's not throwing the kitchen sink at things and doing things that are just a waste of money, but produce lots of paper. They never have any impact on design because you've got thousands of pages of familiar, and tables, and foot high. I see that they sometimes give to the aircraft certification people at the FAA, just to show this giant thing that they've built. And again, the problem is doing the right thing. It costs less to do the right thing than to spend all this money doing stuff that's useless.
Quick question on, I think you touched it at the end of your presentation, cybersecurity. How would you apply a Sdpa approach to the cybersecurity analysis, vulnerabilities or what? Yeah, I'm very interested in that part.
Okay, it's the same analysis. If you think about cybersecurity in terms of mission assurance, again, we're not talking information here, people stealing. There is people trying to steal massive secrets, obviously, but we're talking about, if you're talking about cybersecurity in the program itself, what we're talking about is that we want, how do I think? Look, it doesn't matter whether the loss occurred because the operator, the human, did something accidentally, or the operator was tricked into doing it. We still have to protect ourselves against doing that. And so the the issue is that in each of these, we're trying to maintain the services, the critical services, the critical functions. And so we treat it identically. They do the same thing for safety and security, which means that you cut the analysis in half for both of them because it's the same analysis. All we do is at the end add some more scenarios for security. We identify the same unsafe control actions. You still, don't want the brake. You want the brakes to fail in your car, whether they failed accidentally or there was a design error in the thing, or somebody came in and tampered with it. We still have to have some way of stopping this car, and in case the brakes aren't working. Trying to something simpler than space, making up something for space right now, but it's the same thing. And this is what they're doing again on this replacement of the Minuteman missile system. Again, really complex program. As you can imagine, this is one of the Air Force's big programs right now. They're using Sdpa only. They've stopped doing everything else, and they're doing it for safety and security. And it's early, so they're first just developing the requirements for safety and security to build these things in from the very beginning into the design, find the constraints that need to be imposed and impose them in the design. And they're loving it. And it's exactly the same. Safety and security in this respect can be treated identically.
Thank you.
I had a question.
That is very interesting.
I had a question. Did I hear you say, Nancy, that Boeing has incorporated the Sdpa process and they're using it now, or they're in the middle of implementing that?
Boeing has been using it for about 10 years.
Oh.
Boeing Defense, not Boeing Commercial, not Boeing Space.
Okay.
Boeing Defense. What's his name? O'Donoghue. Age I remember, forget name. Dennis O'Donoghue, who was head of Defense and Space, fell in love with it and tried to get people to use it on their project and imposed it on. And so many of the defense projects actually used it. This is where they say that they've saved an astounding amount of money, because what they did was they showed that by using Sdpa early and then comparing that the requirements they get from their normal processes used on it, that they were saving, that they were finding things early. And so instead of getting them late, the problem at all these people is you find the errors late because you have to have a design. Once you've got a pretty concrete design to analyze, it's very hard to change it if you find a problem. So you try, what do? You try and fix the design, add more redundancy, which adds more weight and probably isn't going to work anyway because you've got all these common failure modes in the thing. So, but there's not much you can do late. And so if you do it early, and so they compared the cost, the things they found early, using their standard techniques, using Sdpa, and then they used historical data to show how much it would have cost them if they found them later, the same problems. And they were finding they were saving that 15 to 17% of the total cost of the project by using Sdpa. For example, one military defense system, it was about a $900 million contract and costs for the whole system, and they claim they saved $127 million by using Sdpa on this. I mean, these are significant cost savings. And again, it's not a matter of doing more. It's doing the right things, doing things that are useful instead of just things we have always done. So we do it, keep doing it. Well, we've always done that. We'll keep doing it. Somebody says that apparently they did not use it for the 737. This is true. Boeing Commercial has never used it. The FAA is I don't know how much I can say about this. It was used by the FAA in the recertification. After the accident, the FAA used Sdpa to try and find problems with the MAX and found lots of new problems that they didn't know about that weren't involved in the accident. And they have us teach, we teach classes to the FAA every 6 months, FAA certifiers on how to do Sdpa. The changing and allowing Sdpa to be used for airworthiness certification is a big step. This is a giant step. People at the FAA in charge tell me that's what they're going to try and get through this year. But the companies, it's very hard to get people to change what they're doing. There are companies doing it. There are standards that are now being voted on for Sdpa, for the FAA certification effort. And yes, somebody wrote, that this would have found it, absolutely. Would have, could have found it. Hindsight, I don't want to say after the fact. It's just unfair to say they would have found it. I don't know.
So are you saying that
they could have?
Yeah. So are you saying that Boeing Commercial is now trying to implement the Sdpa process, and even though it's hard to get people to change their ways, especially old people, which I can't believe, but it seems like if the Boeing space areas are implementing that and they have a very good success rate, it seems like some of that should seep into the commercial areas, and then they realize that due to the 737 MAX problem, they have to do something different than they used to do. So aren't they trying to implement that and make some progress in that area now?
Yes. I only hear rumors. I don't work with Boeing Commercial. I am giving them a talk in a couple weeks, but I haven't worked with them in their aircraft development. Rumor has it, yes, that the people from Boeing Defense after the MAX accident went to Boeing Commercial and said, look, you got to do this, start doing this, using Sdpa and using these techniques. So there have been, but again, I'm not privy to it. Boeing's a very private, secret company, as most are. They don't like to talk about these things, what they do for safety in public, because they'll just get sued or whatever. It all comes up in court. The challenge is implementation. Somebody wrote, what we're finding is the challenge is changing the minds of the safety engineers, the system safety engineers who are used to doing fault trees. That's how they know what to do. This is a paradigm change. They have to learn something new. And we're finding that is really hard. The system engineers love this. And so we go in and convert the system engineers, and they start doing it. Because this is classic system engineering, and they don't have to give up something that they had to do. But Charles Thomas Kuhn is a philosopher. He actually came up with the term paradigm change, and he wrote about this. And it's very hard. It takes generations usually to change a paradigm, because you have to get the young people. So the young people at universities are using this and loving it, and they're going to move into industry. And I'm surprised at how fast it's being adopted. This has been violated Kuhn's thing that it wasn't going to be adopted, but the most vociferously anti-change, against Sdpa and against change has been the system safety engineers, not the system engineers. And when we go in and teach a class, one of the things that almost always happens, we we spend the morning describing how you do it, walking in through exercise, and then they do an exercise of one of their own systems. And the most common comment we get in the afternoon is, oh my God, this is helping me find the unknown unknowns. I finally have a way of finding these unknown unknowns. And what's an unknown unknown? An unknown unknown is something that's just beyond our current tools, right? That we can't find using our current tools. Theoretically, they could be found, and we can find lots of these. The other common thing in the afternoon is, oh my God, we never saw this before in our system, and it's being released in 3 months. What do? We just found this big problem. And what you do is do it earlier. Don't do it before it's through tests and through all your development processes, because it is hard to change them. You have to build our systems are so complex. We can't do what we used to do, build something, find the errors in it, and then fix the errors. You can't do that anymore. You can't start from scratch. You can't back up. It's impossible. So you have to change to this paradigm of build it safe beforehand. And that involves more than just adding a whole bunch of redundancy into the thing, especially for software. Redundant software is unsafe as single software. I mean, the Ariane 5 blew up because they had a redundant software system that was the exact same thing as the primary. So they had the same error, design error in it. You've got to start early. You've got to design these things, which makes it into a system engineering problem.
Thank you.
Just a clarification on Ariane. It was not because of redundant, well, it was multiple failures, and one of them is that it was a reuse of the software that was proven on previous program. And very often that is a leverage on saving, on cost saving. But the issue was that the reuse, it was not exactly applicable. So there was no system integration review of that particular component and whether it was 100% applicable, which in reality it was not. And
right.
that was the inherent error in there. Just
really,
the clarification.
There was a design error in the software, but it was because of requirements. The Ariane 5, it was reused from the Ariane 4, and the Ariane 5 took off at a higher trajectory, which caused the problem when it was used. You're right. They never tested the whole thing together. They didn't do good integration testing. If they had, they probably would have found it, but they used some of the data from the Ariane 4. I actually wrote a paper about this and other accidents, space accidents, a long time ago. Sent it to Mike Griffin, who was a friend of mine, and he was head of the agency at the time. And he sent it out to everyone at Boeing because all of a sudden it came mail from all over the country. Saying, "I love your paper." What? How'd you get it? And so I looked very carefully at these things. And again, every loss is complex. If it were simple, we would have found it and probably prevented it. But the one of the things, and in the accident report they admitted, was that they had assumed that they had, by having a backup to their attitude control system, which was where the flaw was, but the backup ran the same software, and it was a hot standby. So it was actually the backup failed before the primary because they were both getting the data, same data, and they had the same
error, right?
Yeah. But you're right, absolutely. Everything is complex, all accidents. And again, if we only look at one little part of it, we're missing all the lessons we could learn about the other parts that are going to be applicable in other systems. It's not going to be just the attitude control flaw, the same flaw in an attitude control system. It was the whole management structure, the whole analysis structure, the whole belief of how to handle this kind of problem in software. And again, believing the redundant backup system would somehow provide some protection, provide no protection against the design error.
Okay, well, this was an amazing hour and a half. Thank you so much, everyone, for joining, and Nancy, especially huge thank you for your knowledge sharing with us. I hope that you will be able to join us in our future meetings. I'm sure that we need to absorb what you have shared with us, and there will be other follow-up questions. I'm not sure if anyone else has any questions right now to ask, or we will hold it for next time. Charles, Josh, I see that you guys turn on your cameras. Perhaps you wanted to ask questions.
Yeah, I have one question actually. So you've kind of touched a little bit on the different organizations that tend to play different roles in adopting and kind of shifting paradigms like safety versus systems engineers. So I'm in FOD and kind of the mindset that safety is everybody's responsibility and everybody has to play a role in this paradigm shift. So I'm curious, in your experience implementing this in organizations, where do you see like operations fitting into the picture of pushing for this paradigm shift? Where do you see, like, what are the key organizations that you see and that you try to get involved with?
Well, if safety is a system problem, all the organizations, you're right, have to be involved. I mean, a lot of the airlines now are using Sdpa and using CAS for and these ideas from stamp management ideas in their operation. Everyone has to be. You can't take what's really a system problem and only look at one little piece of group working on it. You're going to miss things. So you're absolutely right. I see a question about how did NASA participate in the stamp workshop. Next workshop will be in June. It'll be virtual. And I'll put Svetlana on my mailing list. If anyone else wants to be on the mailing list, send me mail, just levison@mit.edu. And I'll tell you, and we'll send information about it. The last 2 weeks of June, we do it over a 2-week period because we don't want to overburden people. So virtually, so we never have more than about 3 hours a day, 2 hours, 3 hours of presentations each day. And we usually have a lot of tutorials. I'm not so sure we're going to do tutorials this year, but we have videos of tutorials. Past tutorials are available in that, and it's free, by the way. It's always been free. We don't.
And count me in. I will definitely. That's the price you can't beat.
You're right. You can't beat the price. And we'll send out the things so that you don't have to attend the whole thing. You just have to attend the things that will interest you. There will be a lot of, certainly, aeronautics and everything. Nuclear and medical is using it, chemical, not a lot of space. Sorry, because they just aren't using it. This is the one field that's just totally ignored this, and I think part of it is this philosophical difference that got me.
There's always first time. Sometimes, yes. So we just need to start.
Right.
Okay, any other questions? Thank you, Nancy. That was amazing, great. And I put a note that the workshop will be last 2 weeks of June, and we'll just post it on our AAA Houston website, the link, once I get it from you.
Okay.
So then everyone can have access to it. I think it's an invaluable resource, and the more we know and implement or be able to at least advocate for this particular tool to be used within space exploration, that the more people know about it, the more possibility of using actually in reality will be in future.
I think that the way we found to introduce something very new is to try an experimental project. You just try it on something. Don't put it on, no one's going to put it on their critical path. They shouldn't until they tried it. But it's usually fairly inexpensive to do a small pilot, to try it and compare it with what's being done. Sometimes just compare with what's being done in your regular part of that project and do a little side project, shadow project. And we found that that's the best way to get people to change. That they're not going to all of a sudden decide without ever trying it that you're going to throw everything away and do this. That's insane. That would be stupid.
All of our projects are experimental in space exploration. But with that said, yes, that we will see what we can do, and there's definitely a lot of smaller components, some components that we have within space exploration that we have prototypes running, and possibly we can use that as an approach on risk assessment and reliability and vulnerability assessment. So that's definitely a possibility. Okay, well, thank you so much, and we will close this session for today. But again, we have a lot to learn, and we'll just continue with our next Saturday. We'll meet again at the same time. I know it's early for Nancy, as you said, that you're in Seattle. I'm actually in Arizona right now, so we're on the same time, and basically have the same. Right now, it's yes, the light is out, and again, thank you very much for joining, Nancy, especially you and everybody else, and we'll see you next time on Saturday at 8:30 Houston time, Central Time, or any other times, just adjust for your time zone. You have a link, and everyone is welcome. We do not have speaker for next week, so it will be just essentially interaction among members. All the questions are welcome. We discuss everything and anything from the diversity into all the way into space exploration engineering, systems engineering, and so on. And Gary, if you can join next time, I would love to drill down a little bit into the issue that you have touched just on the surface. I have a lot of material, and I have also material to debunk the consumer report that, to me, that particular publication is more of the click and bait kind of type of publication. I have a lot of respect to consumer report materials that they posted before, but for this particular accident, I have to say that it is a click and bait switch type. And we'll discuss it next time. So please do join, and anybody else is interested in any type of conversation that we have on SpaceGeekSpeak. It's pretty much stands for the name. It's a space, it's a geek, and we speak. And please join next time. And for today, thank you very much. Have a phenomenal week, and we'll see you Saturday. Bye, guys.
Thank you for inviting me. Nice to meet all of you.